So, good morning, Year 11s, potential Year 12 students. It's nice to have you on with us. I can see there's 9 or 10 of you that have joined us, so that's fantastic. We're here to talk to you about what it's like to study A-level chemistry at Counterthorpe Lakeland Community College. Okay, so I've got a little quiz for you to kind of warm yourselves up a little bit, get you thinking about chemistry and what you might have learned at GCSE. So there's 3 questions here for you to think about. One's to do with writing formulae. One is to do with drawing some organic compounds, and one is to do with some chemical tests. So I'll give you a couple of minutes just as well while other people are joining us for you to think about what you already know about chemistry. While you're thinking about those, I'm just going to talk to you a little bit about how this session's going to work. So I have Mr. Carr online with me, who's the other A-level chemistry teacher. And if you wish to ask either of us any questions about the course or anything that's come up during the transition work that you've been completing, you can use the question and answer function. You just type a question into the box and we will try and answer it for you during the session. If at the end of the session you have some other questions which we didn't answer or that you think of later, then you're very welcome to email us. And our email addresses are on the transition booklet we've sent out and also on the last slide of this presentation today. Okay. So what we plan to do in the session is, after having a look at the answers to these warm-up questions, we'll tell you a little bit about the course and how it runs. And then normally, if you were in school, we'd do an experiment with you and get you to have a go at doing some science. So with being at home, obviously we are limited to what we can do with chemistry because we don't want to do anything too dangerous at home. I don't think your parents would thank us if you blew up your kitchen, for example. However, we have got a few little practicals that if you got the email from Mrs. Fox, you could have a go at during the session, or if you want to try them afterwards, you can have a go afterwards as well. Okay, so I wonder how you got on with these quiz questions. Don't worry, of course, if you don't get the answers right. The first part of our course is all about getting you transitioned from GCSE to A-level, and we go over those little bits that you didn't quite understand at GCSE. Also, the transition work is aimed to help you with that process as well. Okay, so if we're writing the formula for sodium chloride, it's there, NaCl. For magnesium bromide, it's MgBr2. Magnesium oxide is MgO. Potassium oxide, K2O. Barium hydroxide, bit of a tricky one in there involving brackets. Okay, and then we've got the calcium sulfate, which is CaSO4. So hopefully you got those right. The organic molecules, we've got propane, okay, which is here. Okay, so it's got 3 carbons because it's pro, and it's an alkane, so it's got no double bonds in there. We've got butene, which does have a double bond. You could put the double bond here, or it could be in the middle, or it can be on this side. Any of those answers would be correct, as long as you've remembered not to put the hydrogen in where the double bond is. You can only have 4 bonds around a carbon. Okay, so this is ethanol. Okay, so it's got the OH group on, it's an alcohol. And then this one here is ethanoic acid, which has this C double bond O with an O and a H. Okay, so again, don't panic if you've forgotten these from GCSE. We will go over them again with you. We've also got these here, the chemical tests. Okay, so if you're adding bromine water, that's a test for a double carbon-carbon bond if it goes clear. Okay, A red, oh no, hang on a minute. If you add silver nitrate and you get a yellow precipitate, that tells you you've got the iodide ion. A red flame in a flame test is a lithium ion. And the blue precipitate with sodium hydroxide tells us we've got copper 2+ ions. And then the barium chloride tells us that you would have a sulfate group if you get a precipitate. Okay, so let's have a look at our course. So there is some information in the first transition booklet about this if you've had a look, but obviously if you've got any questions about the course, please do pop it into that question and answer for us. Okay, so we do the OCR A course. There are 2 chemistry courses on OCR, so it's the A one that we do. It's very different to the B course, so be careful which one you're looking at. We expect all of our students to complete the full A-level course, so we don't sit AS exams at the end of year 12. You go all the way through to do your A-level at the end of year 13. So the course is split into 6 modules. Okay, we learn the first 4 in year 1, in year 12, and then modules 5 and 6 plus module 1 is also taught through year 13. So module 1 is about the development of practical skills in chemistry, so that runs all the way through the course as we do different practicals throughout. Okay, so the foundations in chemistry is all about getting you from GCSE standard through to A-level. Touching on all those things you would have done at GCSE to do with mole calculations and acid-base reactions and things like that. And also talks about structure and bonding. Then we've got a periodic table, which and energy, which talks about trends. And we've got things in there about rates of reaction and equilibria and stuff like that. And the module 4, which is the other unit we study in year 12, is all your organic chemistry. So that's building on the ideas of things like alkanes, alkenes, alcohols, all those things that you started to learn about at GCSE and more besides. Okay, so at the end of year 13, you sit 3 exams. Okay, there are 2 exams which are 2¼ hours long. One is all about the physical side of chemistry, and the other side is all about the organic side of chemistry. And then you have a third paper, which is a little bit shorter, and this is all about getting together everything you've understood about the course and being able to answer some questions that are in some different, unique contexts and things. So that's a real test of what you've learned. Also throughout, we complete the practical endorsement in chemistry. Now this isn't examined, it's a bit like coursework. You do the practicals in the lesson and then you write them all up as you go along, and at the end of it you're awarded a certificate for your practical endorsement. This is required by some universities if you decide to do a practical course in the future. Okay, so as part of your first transition work, I did ask you to have a look at some careers in chemistry so you could see where chemistry could take you in the future. And hopefully you found some really interesting ones on the RSC website. It's a really good resource. But just to point out a few key ones, you could go into any side of analytical chemistry. So that could be working in a laboratory. It could be out in the fields, testing water samples, oil samples, things like that. You could be a chemical engineer. So they're people who design new chemicals and new materials and things, quite an interesting career. Something called clinical biochemistry, which at the moment is very important in the NHS. These are our people who are at the moment testing our samples and things to see if people have COVID-19, coronavirus, and also probably designing some of our vaccines and treatments for the future and testing them. So a very worthwhile career. You've also got forensic science, which is testing samples from things like scenes of crime to find out what chemicals are present. You can have forensics in the art world as well to test for forgeries in artworks and things like that. So there's lots of different types of forensic science. Toxicology is all about testing samples to see what people might have poisoned themselves with, or how drugs are working on the body and things like that. Now, a patent attorney is a law degree, well, it's a law profession, and they love scientists because a lot of patents out there are science-based. Okay, so people trying to patent new drugs or new materials or new processes for chemical synthesis and things like that. And with a chemistry degree, you could go into that career as well. So you don't have to go into a science career, you can do something non-sciencey. Okay, so environmental consultant, that will be testing samples out there in the environment, which could be useful for lots of different uses. And again, another non-sciencey one, an accountant. If you've got a chemistry degree, the sorts of skills that you have in analysis, in mathematical manipulation, is really useful for lots of other careers, and accountancy is just one of them. Okay. There are some careers out there that need A-level chemistry, and they are things like medicine, dentistry, and veterinary science. So even though you might think that you need to do very well in biology for these careers, you do actually need an A-level in chemistry as well. Okay. And also pharmacy, and we do get students every year who go on to do courses like this after studying chemistry and are quite successful at getting there. Okay, so why should you come and study with us compared to any other colleges around the local area? Well, at Counters Thought we have small class sizes, which means you get more of a personal learning experience. The teachers get to know you, and they can really help you and understand what it is you get and what you don't get. We have all the specialist equipment that you need to develop the practical skills. Okay, so you might go visit some of the colleges that are really flashy and look amazing, but actually we do have all the stuff that we would need. We conduct lots of experiments. We love a bit of experimentation, me and Mr. Cart, and we try and squeeze in as many as we can in order to develop your confidence. So should you go on and do a practical course in the future, you know what you're doing. Here at CLCC, we also offer lots of support. We're a very supportive department. So every week after school, we do an intervention session for each subject. Chemistry is on a Thursday, and we stay behind and answer your questions, help you with homework that you've got stuck on. Sometimes we run special sessions if something has come up following a test that people are struggling with, things like that. We also have a dedicated science study room with some resources in there that you can use, textbooks and study guides and extra packs of questions. And because it's in science, you can come and find us if we're free and you're needing a little bit of help. And we do have really lovely, approachable staff who are keen to make sure that you do really well. We're specialists and in our subject area. Both me and Mr. Carr have been teaching for a very long time. And we have an extensive knowledge around the A-level chemistry course. In addition, we try to add in some extracurricular experiences to help you widen your horizons and have that little bit extra that you can put on your CV when you're applying to university. So we tend to have a visitor in every year for chemistry who comes to talk to us about a specialist technique that you have to learn about. We don't have the equipment because it's too expensive, but she comes from the university, brings the equipment with her, and we get to use it. So instead of just learning the theory behind it, we get to actually have a go, and she usually does a really nice session which puts things into a context of something like a murder investigation. Okay. Sometimes as well we get to visit the university. Obviously we haven't this year with the coronavirus, but hopefully next year we'll be able to take a group of you to the university and experience what it's like to go and work in a university lab. And every year we take part in the Chemistry Olympiad competition, which is a competition initially at national level to find out who's really, really good at chemistry. They're really challenging questions, so they're quite good for those of you who are trying to get really high grades to actually push yourselves and stretch yourselves to answer some challenging questions. And if you get through, you can either win a bronze, silver or gold award. And those are people who've done really well get to compete internationally against other schools. So far, we haven't had anybody do that, but maybe next year it could be you. So the other reason you should stay with us is we have good results. Okay, so last year, all of our students passed. 62% of our students managed to get an A star to a B grade. And 81% of our students got an A star to a C grade. So compared to the national average, this is actually higher, and we were particularly successful last year. This year, we're hoping, fingers crossed, that all of our students will pass. And again, we've got a good number of students getting their target grades or close to their target grades, and hopefully some of them will be able to go off and study the courses that they want to do next year. So what sort of things might you learn about? Okay, so here's a bit of a snapshot of some of the things you might learn about. These diagrams over here are talking to you about the shapes of molecules. So as well as just learning about the types of bonding, we need to learn about what's the structure, the three-dimensional structure of these molecules are, because that helps us work out how they interact and bond and with other things. Again, we'll come back and look at analysing like we did in GCSE, so making sure we can identify compounds using analysis. We've also got on here stuff about acids and bases, so we come back to that. We have another look at titrations and how we can use those. We've got some environmental stuff in here, looking at how ozone's depleted. Some more analysis here, identifying compounds using a machine that can help us identify it, understanding how to read these traces. And also about synthesizing new molecules. Okay, so using this apparatus, we would be able to prepare something called an aldehyde, which you would learn about. Okay, some other things here that you might recognize. So we look again at rates of reaction. Okay, we've also got in here some stuff about polymers, and I'll come back to that in a minute. We've got energy changes in reactions. Again, that might look familiar from GCSE, and some stuff to do with equilibria as well, so the equilibrium. Right, so as I say, we do lots of practical techniques wherever we can, because that is part of chemistry. It's understanding how to synthesize things and how to analyze things is part of the course. And in places, we do tend to have a little bit of overlap with biology. We do a little bit of biochemistry, looking at things like amino acids and stuff like that, if you have an interest in that kind of area. All right, so Mr. Carr and I were having a real think about what we could do that was a little bit practical with you today, because normally we would get you doing a practical in the lesson. Okay, so we've decided to have a look at the chemistry of plastics. So when we teach chemistry, as well as teaching you about all the things that are in the course, we try to make sure that we put chemistry in contexts for you. So we're always trying to tell you where you would use this, why is this important, where does this fit into our real life. And chemistry and with plastics are everywhere. So they're in your home, around you all the time. You're wearing them, you're probably sitting on some, you know, it's everywhere around you. Some of them are also natural polymers, which is another word for a plastic really, which exist inside your body. So things like proteins and fats are natural polymers that exist inside your body, as is your DNA. Okay, so if you were doing the biology session earlier, I think you learned about DNA. So polymers are long chain molecules, remember. So they're made up of small repeating units joined together to make a long chain. Okay, so the small units are your monomers and your long chains are your polymers. So the first experiment that I thought we could have a go at is thinking about chewing gum. Okay, so I'm just going to show you my packet of chewing gum. If you can see what it says on the back. Now they're a bit sketchy about all of the ingredients in chewing gum. So you've got some things in there like sorbitol and a few other bits and pieces that are basically sugar and flavours. But the main component of chewing gum is something called gum base. Now gum base is unique to each particular chewing gum manufacturer, and they don't reveal exactly what is inside their gum. Okay, it's a bit of an industry secret, but a lot of chemists analyse it and we know roughly what's in there. So excuse me, because to do this practical, I'm going to actually have to chew some chewing gum. So let me start chewing it. The original chewing gums were actually made with natural polymers, things like rubbers and resins that you can get from plants and trees. Most modern chewing gum is made from synthetic plastics. Okay. So hopefully this is probably making you feel quite gross about chewing gum. It always does me. I'm not normally a big chewing gum fan. The most common substance that you find in modern chewing gums is polyvinyl acetate, or PVA. Okay. Now PVA is also the same stuff you find in that white glue that you use in school. Okay. And if you've made slime at home, you've probably used PVA glue to help you make slime. Okay. So when you think about it, it sounds quite gross that you're chewing something that also exists in glue. Now, PVA inside our bodies doesn't really degrade, and this is why we're not encouraged to actually swallow gum. It basically just comes out the other end. But the idea is to spit it away. Now, the whole purpose of chewing gum, what the manufacturers are trying to do, is produce a gum that's chewy, that's rubbery in texture in your mouth. And the reason it behaves like that is something to do with the glass transition temperature and to do with the properties of polymers. Now at the bottom corner, you can see the repeating unit for PVA. So this is the vinyl acetate molecule. The square brackets, if you remember from GCSE, tell you that's the repeating unit. And essentially there's just lots of those stacked together in a really, really long chain. So the glass transition temperature is a really important property when you're trying to think about what your polymer needs to do. So if you want a hard polymer, if you want a really hard one, then you want something which has what they call a crystalline state. And I'll show you a picture in a minute. If you want something to behave rubbery and chewy like a chewing gum, then you want to have a different temperature. You want your plastic to behave in what they call an amorphous state. Okay, so this is the polymer chains. And if you look at the amorphous side, you can see that the polymer chains are all kind of tangled up around each other, a bit like a pile of spaghetti. Okay, so these polymers are very, very rubbery, bendy, chewy, and this is how we want our chewing gum. So, excuse me for being gross, but my chewing gum is very, very chewy. Okay, you can do this at home if you want to. I'm sure you've probably done this lots of times, but it's very bendy. We can shape it into all sorts of different shapes. Now, if we go back to this picture, you'll see the glass transition temperature of PVA is around 30 to 40 degrees. Now, obviously, your mouth temperature, the human body temperature, is 37 degrees. Okay, so at this point, you're above the glass transition temperature. So this means it's going to behave like a rubbery material. However, if we go below 30 degrees, the chewing gum will stop being rubbery, okay, and it will become a crystalline state. So you're forming something that has lines where the polymers are lining up against each other. And what that does to the property is make it very brittle. So if you do this at home, you can put a bit of chewing gum into your freezer and freeze it hard. Here's one I prepared earlier, and it becomes quite brittle. Okay, and if we were to try and pull this about, it doesn't pull anymore. And if I was to take a hammer or something to it, you'll find that it's very brittle and it fractures. So this is the reason why, if you've ever got chewing gum on your clothes, people say to you to put it in the freezer. Because when you put it in the freezer, the chewing gum turns brittle and you can literally just break it off. And also, quite disgustingly, if ever you've touched the chewing gum that's stuck to the bottom of the desks in school, you'll know that's quite hard, okay, because it's gone below that transition, below the glass temperature. Okay, so I'm going to hand you over now to my colleague, Mr. Carr. He's been sitting there all along, listening to me. And I'm going to ask him to have a bit of a chat to you about Lego plastic. Okay, and his experiment is to do with Lego and acetone. So just give me a second to kind of swap us over. Hang on a second, Mr. Carr. I'm just going to put you on live first if you want to introduce yourself. And I'll find your video.
Good morning, everybody. This is kind of weird because it's the first time I've actually been live doing this. So welcome to A-level chemistry. With some of the information that you've been given prior, you've probably been asked to do some experimentation at home. And in the video that you're going to see in a moment, over the last 48 hours, I bought myself some small Lego kit and some acetone. And what you do is you get your little Lego person, you place it into the acetone, and over a period of about 24 hours, the whole thing starts to dissolve. Now, a lot of people on YouTube say that, oh, you can get it to melt. It doesn't melt. If you heat something up, you can take it past its melting point, and most plastics and polymers actually behave in the same sort of manner. Now, Lego happens to be a combination of three monomers. The first of which, I'm not sure if you guys can see this terribly well, but I'll do my best. So if you can't see it, please make a question in the Q&A, and Dr. Francis will let me know whether you can or can't see it. But essentially, when you were doing GCSE, you did about hydrocarbons, and that's all organic chemistry. Now, I know a few people are going to be a bit scared about this, but don't be, because it's really, really easy. It sounds hard at GCSE because it's kind of rushed through with everything else. At A-level, we really take our time, and really, quite frankly, it's the easier aspect of chemistry. I know you might not believe me at the moment, but honestly, it is. So if we recall just the polymerization and addition polymers, you know that if something has a double bond, like this particular molecule here, this double bond can open up and become part of a polymeric chain. Now, this part here is essentially acetyl nitrile. Now, the naming of it, I'm not going to go into any details with at this point because the nomenclature is irrelevant, but during your course, you will be shown how to name all of these different chemicals and how to systematically name polymers. The next part of the repeat unit that makes up your Lego bricks happens to be from styrene. This is a benzene ring attached to essentially a carbon-carbon double bond. This carbon-carbon double bond opens up, it can join with this carbon-carbon double bond, and you end up with the start of a long chain molecule. And then lastly, what you happen to have is this section. Now, this section comes from two molecules. In fact, actually, I've drawn the monomer slightly incorrectly here. This double bond should be in the middle, and there should be one at the end here. Now, each of these three, if you were to make the polymer on its own, so this one, if you were to just have an addition polymer with just this molecule, you would get cling film because it contains isocyanates. This molecule here happens to be polar. Now, you will have been taught from year 7 up to year 11 that something will dissolve if it is polar. Now, sugar will dissolve in water, just like salt will. Salt, we know, has got electrostatic interactions, positively charged sodium, negatively charged chloride ions, but glucose, which is all covalently bonded, is also polar due to something called the electronegative effect. Now, I'm not going to go into huge detail about it, but it's this fact that makes this really important as to why it is that your little Lego piece will not be terribly well, won't be very strong in a couple of hours after you've put it in acetone. So in this case, if you just had this, you would get cling film. In this case, you would have polystyrene, and in this case, you would have a rubber band. So each of these three, if made into an addition polymer, would give you a different type of plastic. So, but if we put them together and have them as a repeat unit, then you end up with Lego. Now, Dr. Francis, if you could play the video. This is a short little video that I started, I guess, Saturday morning, and I finished it this morning so that you guys can have a look at it. Enjoy it, and I'll be right back. I'm not sure if you guys can actually see me or not, but anyway, so I hope you've enjoyed that. And just a couple of things about that is the reason why acetone will dissolve your Lego or your plastic is because it happens to have this, what we call functional group. And it's this essentially a cyanide component that gives the whole molecule a polarity. So therefore the acetone can get in between these long chain molecules and start to dissolve it. The best question that one of my nephews asked me over the weekend was, Uncle Paul, why is it that that it doesn't dissolve in the container? And the reason for that is because the container is made of polypropylene or high density polypropylene, and therefore there is no polar parts to the long chain molecules. If you look on the PowerPoint that Dr. Francis has put on, it's used also when people are building huge structures at Legoland. They have this paint, but it's not paint, it's just acetone. They cover the top bricks in it, they put the bricks together. As the brick starts to dissolve within the acetone, it becomes very sticky. They place the next brick on top of it, and therefore you can have these giant structures and they don't fall to pieces. So some wonderful plastic chemistry, some wonderful organic chemistry, and it's very easy to understand. Thanks very much. Dr. Francis, if you'd like to take over, that'd be cool.
Okay, so I'm just going to see if I can get me back on to the screen. It's all new technology for us, this, guys. I've still got Mr. Carr on there, so let me see if I can work out how to put me back on the screen. Sorry, Mr. Carr. No, I can't get rid of you, Mr. Carr. Right, okay, so, oh dear. Right, it might help to put me back on the screen first, I think. So let's just do that first. So anyway, so it's me and Mr. Carr who teach the course. I'm in charge of chemistry. I'm head of chemistry at CLCC, and Mr. Carr and I both teach year 12 and year 13, and we love doing it. It's our favourite part of our job. Thanks so much for some of the questions we've sent in so far. Hopefully we've answered some of them for you. I know one of you's asked if you can study the applied science alongside chemistry. Now, a lot of that will be to do with how they schedule the units together, the different topics rather in the timetable. So the best person to ask there would be Mrs. Fox, because she'll know more about that than us. So if you want to pop her an email about it, you can ask her. Okay, so I've lost my PowerPoint at the minute, so just give me a second. In fact, I don't really need to show you the PowerPoint. What I'm going to do is the third experiment that I've got for you, which is about making plastic from milk. Now, if you've got younger siblings or cousins or whatever that you live with, they would love this experiment if you want to do it with them. I did it with my kids the other week at home. They're both primary age. But what I've done is I've taken, there's about 150 mils of milk there. It's about a cup of milk, basically. Now, I just nipped and microwaved mine while Mr. Carr was showing his video. You only need to put it in the microwave for about 20 to 30 seconds. And heating it up is just going to make the reaction go faster. So what you then need is a bowl. So any bowl will do. Pour your milk in the bowl, and then you're going to add vinegar. So milk contains a protein, and if you remember, I said proteins are natural polymers. It's a protein called casein. Okay, so in milk, normally what happens is one part of the casein is what's called hydrophobic. So they form these kind of globules. Okay, if ever you look at milk under a microscope, you would see these little globules inside the milk. Okay, so most of milk is water. But in between, there's fat globules. If you have full fat milk, if you've got the skim milk, they take out most of the fat globules, but you still have these protein globules. Now, the protein chains arrange themselves so they kind of stick out of these globules, okay, like this. Now, the the bits of the protein chains that are inside the globules, they're surrounded by calcium phosphate, which is a compound that's present in milk. That's why we drink milk, for the calcium. Okay, so the inside of these protein chains are what's called hydrophobic. So they don't like water. So they clump together and kind of protect themselves away from the water. The tail's sticking out, so that side of the protein, that's what's called hydrophilic. They love water. Okay, so they face on the outside. So normally in your milk, this is what's going on. And these chains contain carboxylic acid groups, but they are deprotonated. Okay, so they have no hydrogens on them. When we add vinegar, or we add some kind of acid like vinegar, then what we're doing is we're adding hydrogens to those chains and we're protonating them. And by doing that, what happens is you are causing these globules to be attracted to one another, and they cause formation of huge globules or clumps. Okay, and this is what they do when they make cheese as well. Okay, so they're separating the curds from the whey. So what we do, we're going to add a couple of tablespoons of vinegar. Oh, it's squirting out all over the place. Okay, so any vinegar will do. If you've got cider vinegar, wine vinegar, just normal malt vinegar, you can do it with any. It's just the fact that you're adding an acid. Okay, and when we stir it, quite revoltingly, it goes all lumpy. Okay, it looks quite disgusting. Okay, so I'll show you. You see that? Kind of, all kind of lumpy. Okay, so that's what's happened, is we've caused those casein globules to all clump together into great big clumps. And as I say, it's similar to how they make cheese. They also use something called animal rennet sometimes in cheese, especially if it's a non-vegan cheese. And that does the same thing. And rennet's basically cutting up the proteins, and it kind of causes them to globule together. So once you've got that, what you have to do is sieve out the liquidy stuff. So I'm just going to do that at the sink next to me. Make sure you wash your mum's sieve afterwards, or your dad's sieve, whoever you borrowed. But what you end up with is this kind of cheesy type consistency stuff. Okay, now you can give it a bit of a rinse if you want to. For time reasons, I'm not going to at the moment, but you can do. So you then need some kitchen paper or tissues or something like that, and you tip out your globby, horrible plasticky stuff. Okay, if you really wanted to, if you're doing this to kind of show off with your little brothers and sisters, you can always add a little bit of food dye to it before you add the vinegar, so you could have pink or blue plastic if you wanted to. So what you then do is try and get rid of as much of the moisture as you can. Okay, and if you've got some nice cookie cutters or something at home, I found a star-shaped one. Okay, you can press your plastic that you've made. It looks a little bit like, kind of, I don't know, a bit gross really, but it's a bit like cheese. Okay, if you've ever had feta cheese, it's a bit like that. Okay, so you're going to squash that inside your shape, and then you need to leave it for a couple of days to dry out. Okay, so if you put it on a plate or something like that in your window, you can leave it to dry out, and you'll end up with, in a couple of days, something that looks a bit like this. So this is one I made with my kids the other day. It's a really hard plastic. Okay, it goes completely solid. Okay, and that's plastic made from milk. Now, obviously, the advantages of being able to make plastic from materials like this, these would be what's known as a bioplastic. And bioplastics tend to be more biodegradable in our environment. So bioplastics is something that we are looking at in terms of the future of plastics, or one of the future of plastics are either bioplastics, so made from biological resources, because obviously we're going to run out of oil, which is what we make most of our plastics from, or plastics that are biodegradable as well, ones that can be broken down. Okay, so I hope that you guys have had a bit of fun kind of watching us being silly and having a go at some chemistry. Obviously, the experiments we would do in a real chemistry lesson are a little bit more exciting than that, but not things that you could do at home. I really hope that you'll have a go at some of these experiments at home, even if it's just putting your chewing gum in the freezer. Okay, it is worth a go. I'm going to see if I can find my PowerPoint again, and I'll also have a quick look, see if there's any questions that we haven't answered for you yet. And then we'll also talk a little bit, I think a couple of you have asked questions about textbooks and resources and things that you have. So we'll have a look at those in just a second. Just having a look at your questions. Just my pointer. Okay, so let me just check your questions. I've got a few of you saying hi, hello. I know it must be weird for some of you who've not been in school for so long. I guess it's nice to see familiar faces today at all these sessions, for those of you that are here. Okay. Right, let's go back to the PowerPoint again. Mr. Carr, is the PowerPoint on the screen? It is, right, okay. So where did we get to? So this was the structure of casein. I was going to show you these circled groups here are the ones that get protonated when we add the acid. Okay, and that's the little micelles that I was drawing for you on the board. Okay. So when we do the course, we have what we call the A-level kit. So what do you need to do the course? Well, we have textbooks in school. Okay. You can see the one at the top there on the PowerPoint. Or if you can see me as well, this is our AS book. Okay, we provide these in school, so we have copies for you that you can take out during the course, so you don't have to buy any. Some students do try buy their own purely because they like to write in them and highlight things, which obviously if you want to do that, that's fine, but you don't have to. You can borrow the ones from us, but obviously you can't write in those. Sometimes it's worth getting hold of students who've just finished the course to see if they've got any books they might want to sell secondhand if you do want to get your own. Okay, there are also some revision guides that are available through school to help you throughout the course, and also they have like little practice books as well where you can practice questions as you go along, but again that's up to you, you don't have to buy those. The things that you do need are your own folders, paper, and dividers are helpful because every different topic, if you have a divider and you can separate things out and be organised right from the word go. We also provide you with a couple of exercise books. So one of which is for doing your practical work in, and one we tend to use for you to complete your summary questions in. So every part of the textbook, each page spread, at the end of each section has some summary questions, and we ask you to complete those at the end of every section after every lesson so that you kind of going away and reflecting on what you've learnt. And so we give you a textbook to do those in, and we will check. One of the things we do is check that you are doing that, so make sure that you are on top of your studies, because for every hour that you spend in the classroom, we are expecting you to spend an hour outside of the classroom, either reviewing what you've learned that lesson or practicing questions from that lesson, or you could be making a revision resource for later or starting to read ahead to the next lesson so you know what's coming. Okay, so we try and develop those independent skills with you early on in the course, because those that do get the hang of the routine of it do tend to do better in the long term. Okay, you'll also need a scientific calculator. So obviously if you're doing maths, you will be required to get a graphical calculator, but you won't be able to use one of those in a chemistry exam. So you need to have a separate scientific calculator that you can use in your science lessons. Okay. So after this session, you will be receiving a second transition booklet that'll be coming through via Miss Challoner, and we have tried to give you some different activities in there. So the first transition booklet focused mainly on ideas that you'd encountered at GCSE that I wanted you to just have another look at in case you hadn't quite grasped it. This one introduces you a little bit more into some new ideas, some things we're going to start looking at in year 12, one of which is atomic structure in a little bit more detail. Okay, so you'll be able to find out about that. There's also a nice task in there to get you to look at some more chemistry in context. So we've discussed some chemistry of plastics with you today, but there's lots of other exciting chemistry out there that you could have a look at, see where chemistry is actually used in real life. And we'd like you to choose an area and make a poster on that as part of the transition work. And what would be really nice in the first few lessons is we're going to share those posters with each other as a kind of way to get to know one another, and why we might want to study chemistry and what we find interesting about it. Okay, so if you've got any further questions, I'm just going to have another look through your questions to see if there's any we haven't answered. If you've got another one, we'll hang on for a few minutes so we've got a chance for that to come through, because I appreciate there is a delay. And we'll see if there's anything outstanding left to answer. But as I say, you can email us if you want any further help, and our email addresses are in the transition booklet. What we got, Mr. Carr? Any interesting questions for us? The book? Yeah, sure. So this is the textbook. Oh, there we go. This is the year 1 textbook. So if we have a look at something that you've encountered before, let's just have a look. Okay, so this bit's about the periodic table. Okay, so you can see the textbook there. It's got some facts in there. It'll have pictures. Sometimes it has extra information in little boxes that are in to do with context. And then at the end of each section, there is summary questions that you can complete to show to check your understanding, and the answers for all of those are in the back of the book, so it enables you to check almost instantly whether you get something. There's also at the end of each chapter a selection of past exam questions or exam style questions, so that you can have a go at applying your knowledge to questions you might come across in an exam. So we do those at the end of every topic so that you get that practice as well. And we do have other sources of questions, worksheets and things that we can give you on top of that, so you've got plenty of opportunities to practice things. Okay. Generally for sciences, those of you asking about entrance grades, it's normally a 6 to do any of the individual sciences. If you just miss out slightly, then sometimes we have a bit of a chat with your teacher, whoever they were, and discuss whether we think you might be able to have a go at the course. But usually it's a 6. If you're getting a 5, you can always apply for the applied science course with Mrs. Fox and Dr. Derry. And if you want to know more about that, if you missed the session earlier, you can email Mrs. Fox about that and ask a little bit more. They cover all 3 sciences, so they do biology, chemistry and physics, and it's a bit more applied, so it's coursework based as well. So if you're not that confident with exams, you get anxious about exams, then you might prefer that kind of course. But it will also depend what you want to study at university, okay, because some courses would prefer you to have the individual A levels, so it's something you need to carefully consider. And hopefully there'll be someone from science, if you're at this school, if you're at CLCC, down in the hall when you get your results, if you're coming into school for them this year, that you might be able to talk to about your options once you've got your results in. Any other questions I've missed, Mr. Carr? I'm struggling to click on it.
Tutor also recommend that they seriously consider what they want to do professionally, and really look, is an A level in chemistry required or advantageous?
Yeah, I think I mentioned that a minute ago actually. So I don't know whether anybody else has any further questions. We think we've covered everything, but like I say, if you do have any questions, just email us, or if it's generally about sciences, then you're best to email Mrs. Fox. So all our email addresses end with @clcc.college. So if you wanted to contact me, I would be cfrancis@clcc.college. Mr. Carr is pcarr at clcc.college, and Mrs. Fox, who's head of science, is kfox at clcc.college. So hopefully between us we can answer any of your questions. The deadline for choosing subjects, you can literally decide on the day you get your results, and even probably in the week afterwards. We've had students change courses in the first week of their course, so right up until the very last minute you can decide once you've got those exam results. But if you wanted to check, Mrs. Challoner, who's head of sixth form, is currently online as well. She's taking messages today. And I think on the main page that you signed in on at school, it's got any like a texting number to text to, or you can email her to ask questions about when you finally can join the courses. But yeah, usually we've had students who've decided right at the last minute, once the literally on the first day. I mean, if any of you wanted to let us know how you did in the little warm-up quiz, you can always pop your name in a message in the question thing and tell us what your score was, if you want to do that before you go. But I think if we've answered all your questions, we're going to sign off in a couple of minutes. It's been really nice to have so many of you online, and fingers crossed for you for your GCSE results, so you can come and join us on the course. Okay, so I'm just going to say bye. So thanks for joining us. Mr. Carr, did you want to say bye-bye? Hang on. I'll fiddle about with it now. Hang on. No, it doesn't want to put you on there. I'll tell you what, I'll just move out of the way, do our 2 metre social distancing.
Thanks very much, everybody. Hopefully we'll see you in literally about 7 or 8 weeks. Stay cool. Thanks very much. Okay, so we're going to sign off then. Thank you, guys. Bye.